Hello to everybody. Welcome to this winter edition of the Spotlight Seminar by the Italian Association of Artificial Intelligence. Winter edition. It is really a pleasure for me to introduce the novel committee that helped me and the organization to define these seminars. So first of all, I would like to invite the Vice President of the Italian Association of Artificial Intelligence, Chiara Ghedini. And then we have Luciano Serafini and Antonio Lieto. So I really thank you for the efforts in organizing this series of seminar. And I would like to leave the stage to Chiara for presenting our very distinguished guest today.
So thank you, Gianluigi, and welcome everybody also from my side. So it's a great pleasure for me to introduce today Paolo Traverso. Paolo Traverso is the Director of Strategic Planning at Fondazione Bruno Kessler, which is one of the first research institutes, or the first research institute in Italy, started working on AI. From 2007 to 2020, he was the Director of the Center for Information Technology in FBK, and it was one of the big centers working on computer science and AI with about 350 researchers. He joined FBK, which at the time was called IRST, in 1989, after working in advanced technology groups in different companies. So he didn't start with the traditional career of, let's say, graduating, doing a PhD, and then doing research, but he tried, let's say, he worked in companies, in consulting, at an international level. And then somehow he got captured by research and started working in Trento in FBK, and he basically spent his entire research life there, but maintaining really an international flavor. I mean, his contribution in the planning area are internationally recognized. He's the author of two of the reference books on that. He was nominated and URI at the time, well, ECAI at the time, now URI Fellow, for pioneering work in the field of artificial intelligence and outstanding service to the AI community. He's also in the scientific advisory board of the FKI. And he now, let's say, I would say, knowing him personally after many years of management, say, he's really going back to research, and I think he will give now today a talk on his view of what are new interesting things to do in the planning domain. So with great pleasure, I would leave the floor to you, Paolo.
Thank you, Chiara. Thank you, Chiara, for the very nice presentation. Thank you to the board of the Italian Association for Artificial Intelligence. Very happy to be here today and to talk with you about this topic of planning and acting to learn. Actually, when I sent my abstract for this talk, I had in mind to give a presentation about recent result on this topic that I have achieved joint work with many good friends, many good colleagues. But then I've seen a description, I had to look at the description of this Spotlight seminars, and I've seen a strong emphasis on future challenges, on open problems for future direction of research. So I changed my mind, and I decided to give a presentation about challenges on this topic of planning and acting to learn. And I hope this will not be disappointing. I will talk more about problems, open problems, and then solutions, challenges, then results. But I believe this could be interesting. And while the work on planning and acting to learn I've done with very good joint work with very good colleagues, this idea about the challenge come out of an intensive, very lively, I would say even passionate period of discussion with Luciano. So this is what I'm going to present today is really joint work with Luciano. And let me start my presentation with the most famous book on AI. So Stuart Russell and Peter Norvig, in one of their editions, they define artificial intelligence as the study of agents that are able to perceive in the environment and are able to perform actions. Now, if you consider the most usual and typical and traditional, I would say now, way to provide an agent with learning capabilities for perception. The most well-known approach is by pre-training. So usually the idea is to pre-train once for all offline a set of different perception models from hundreds of thousands, and now we know even billions, thousands of billions of either annotated or not annotated data, for instance, from images or other sensory data. And what about learning how to act? Also, in this case, the most usual approach is by pre-training. I would say that the most well-known and successful approach is reinforcement learning, where we used to train with a set of traits, typically through a simulator, in order to provide learning capabilities on how to act. In this picture, I have the very famous 40 days of training of AlphaGo Zero. That was a very successful, and really surprising result. Of course, my question is not whether pre-training is useful. Of course it's useful. It has been very successful. My question is different. Is this really all what we need? Is it really enough, for instance, to build agents that are able to work in an embedded real-world environment, open-ended environment, where the agent has continuously to live and the environment is partially no, like in this very simple picture where you see we have a very simple agent, even without manipulation capability, but this agent has to understand there is a little girl in front of him, of her, how it is, and there is a book that is open, then the agent even doesn't know how many books there are. For instance, here there are other books, and should discover all of them while living in the environment. There are different kinds of chairs, they are even very specific of this environment. So if I go back to the question that I asked, is really pre-training all what we need? People researching psychology, the answer for them is no. It's a very well-known experiment in the 60s that has demonstrated that a cat, because the psychologists do this kind of experiments, a cat that really acts, moves in the environment, really learns much more perceptual capabilities, better perceptual capabilities than a cat that instead is just not acting, not living, not moving in the environment. And the conclusion is there is a compelling evidence that perception in humans and in animals is an active and explorative process. And think about all the work on the area in robotics, on the area of interactive perception, where they say really learning how to act and learning how to perceive in the world. There are two very interrelated processes that really influence each other. They are really tightly connected together. So I believe it's important to try to build agents that are autonomous in learning, updating, improving, and also changing, questioning, challenging, and they are improving their perception capabilities and acting capabilities at the same time by exploring the environment, interacting the environment. And even something more, it would be an important goal, not only to build agents that are able autonomously to learn, adapt, and extend their model, but also to automate in some way the way in which they can learn. They can collect data, new data, to learn and improve their capabilities. Exactly in the same way like these two children are doing while they are playing. And even more, to automatically evaluate the quality of the prediction, the learned model, and identify the situations where it's possible to learn more and to have predictions that are correct. So the challenge that I'd like to discuss with you today is the challenge to build agents that autonomously learn, adapt, extend, improve both their model of the environment as well as their perceptual capabilities by planning and acting, living in the environment. And here comes the outline of my presentation. So I spend most of the time of this talk on the challenge, but I'll give also some very preliminary ideas of how to address the challenge. And then, of course, these ideas that I present today don't come out of the blue, but there is a lot of joint work with very good friends that we have done to try at least to address partially this challenge. And I'd like to conclude my talk with a claim that what I'm going to present today is really a much larger and broader important problem than the simple examples, kind of toy example that I'm going to show you to talk about this challenge. So, okay, let's start from the challenge. In order to be a bit more concrete about what we mean by this challenge, we have really to understand which is the right model an agent has to have in order to address this challenge. And what I believe that the agent needs three key components. The first component is a symbolic model that represents actions and how they affect the environment. This is what we do in planning, but here is very important. Here is very important because if we have really to take for serious what people in psychology and robotics say, is that actions and perception influence each other, and the way in which you learn them influence each other. So the agent should be able to decide which action to do, to perform, in order to reach situations in which it's possible to learn, it's possible to change, to update both the perception and the symbolic model itself of the environment. Then, while it's reasonable that an agent can plan, act, decide the action at this level, symbolic of abstraction, of course, in most of the case, perception are at a different level from different sensors, very heterogeneous sensor, camera, microphone, this kind of thing. So we need a kind of common shared space, a latent model that is able to represent this heterogeneous, often high throughput, multimodal sensor data. And we believe that we need two object latent models. One that maps individual symbols in the symbolic model that represent objects in the environment through a latent space where representation are able to really allow the agent to represent the same object, but in the different ways in which the agent can perceive this object. And then we need another latent model that here we call property latent model that maps different kinds of symbols representing properties into functions that predict if an object in the environment has such property using the latent model. Now, I will say much more about what we think and what we believe should be these three models. But before I get into these details, I'd like to state and to discuss with you a very important property that I believe these three models must have. They must be learnable. Here, by learnable, I mean they should be learned, so they should be updated, they should change while the agent lives in the environment. All three models. So here we cannot base our work on some assumption that is done many times in work in neurosymbolic reasoning, where you say, okay, I trust the symbolic model and I use the symbolic model to learn the perception. There is no perfect symbolic model, and neither the other way around. I trust my perception capability, I trust my object classifier as it would be perfect. There is no perfect object classifier, and then I abstract it to a symbolic model. So we should, for instance, be able to update the signature of this symbolic model. Why? For instance, if I represent with individual symbols the object in the environment, the agent should discover this individual symbol, this object, while it lives. So it's not fixed. It changes. The signature should change, as well as we should be able to let the agent to change the specification of actions and also the latent models that I have just introduced. So let's start from the first symbolic model. And of course, here we have different choices. What we have chosen is a relational MDP. Why? Because it has all the elements that we need, but could be a different choice. But why I say it has all the elements that we need? It has constants that can be used to represent objects in the environment, like in this very simple example, we have 4 constants representing 4 different objects. Then it has predicates that represent with atomic formula properties of object in the environment. So I have an object that is represented by C1, the constant C1, that is a book and is closed. C2 is a book and is open, and so on. And then, of course, I need to represent, like we do in planning, different states of the environment. This simple example, the state is represented by the atoms that hold in this state. Like in this case, we have two objects that are a book that is open and a box that is not open. As we usually do in planning, the state is represented by the atoms that hold in the state. And now we have to represent actions. Now, here we need a representation. We have chosen an MDP, so we have a probabilistic representation, stochastic representation. You see that tau A is the probability that if I execute an action over a constant C in a given state S, then I get to a new state S prime that has where different atoms hold. But one important characteristic is that this representation should be lifted, what we in planning call action schema. You see the red A of Z. Z is a parameter that can be instantiated to different constants. Why we need this parameter? Why we need a lifted action schema? Because we don't know how many constants, we don't know how many objects we have in the environment. So we cannot define a ground representation. So we need really to go an abstract level. Then we need to define this probability that I mentioned before, tau A. And one way is, for instance, in this way, similar to what we do with dynamic Bayesian network, where we have the action open over Z that represent an object. Then if the object is closed, you see, is open, Z is 0, and cannot be open, then I just leave a very low probability that I managed in any case to open the object. Could be 0, but I have this degree of uncertainty. Then the second line, if the object is closed and can be opened, then I'm very optimistic. 0.9%, very high probability that I manage to open it. And then if the object is open and can be opened, I just say that it's very rare that I will make a mess, and while trying to open something that is already open, I close it. But this is just an example. What is important to understand here is that in a different environment, opening could behave in a completely different way. So this probabilities distribution should be a parameter that the agent should be able to change and to learn. And we call tau the set of all the parameters of all the actions in the symbolic model. And here we have a very simple graphical representation of the action that I have just described. You know, 90% of the time I imagine to open the object, and just 10% the action will fail. But this is a simple example. So let's go now to the second model that we need, the object latent model. As I mentioned before, perception usually, and many times, are done at a different level, at the level of different sensors like cameras and microphones. So they are really heterogeneous, multimodal, and with a high throughput. So I need a common internal latent space. And let me provide a definition. This is also a choice, but a definition of what is this object latent model. The important point here is that it maps a constant C that in the symbolic model represent an object in the environment, and we have chosen a normal distribution that return, and this is just a choice because it's common, it's a good mathematical property, but the choice could be different. Return, in any case, what is important, the likelihood of perceiving an object, an observation such that gets embedded into X when observing the object that is represented symbolically by the constant C in the symbolic model. And according to this definition, one way of implementing an object latent model, there can be different ways, but one simple way is to a variational autoencoder that depends on this parameter that you see here, eta. So we have a second set of parameters to be learned. We have tau, we have eta. And according to eta, we can encode an observation into a normal distribution, then we can sample this normal distribution and we can decode into an observation. Now, one could argue, why do we need this generative model? Why do we need to do the decoding? We need because the agent needs to live in the environment, to interact with the environment in the way of the data that is perceived by sensors. So, for instance, let's assume that in the simple picture that I've shown with the agent, the little girl asks a question to the agent, and the agent has to reply through the voice and not through the latent model. So we need this kind of decoding, but the same for images. But we will see there is a further reason that I will explain later. But let's for now focus on this second set of parameter eta. We have a set of parameters for all the constants on the symbolic model. And here is a simple graphical representation of the variational autoencoder. We have, according to eta, an encoding, for instance, in this case, not of speech, but in this case of images. And then we represent this through a normal distribution. Then we can sample it, and we can decode it and generate a new image. A good property, an important property of this object latent model is the ability to represent the same object. Since in the symbolic model, we have just one constant, C. For the object when, for instance, a book that is closed and the book that is open, or for an object that is seen by the agent from a different point of view or under a different intensity of light. And so this should be represented in the same way. Itself, this may be a challenge, but of course there are techniques to do this. But the real challenge will be when we put this kind of challenge together with the other challenge about learning the other model. Let me so go on and describe very quickly the third latent model, the property latent model, that maps symbols that this time must represent properties. And in our symbolic models, the properties are represented by predicates. So we get a probabilistic model that is again parameterized. You see here there is another set of parameters, theta for each predicate P, that returns the probability of P being true over the constants in the symbolic model representing object in the environment, given the samples of the embedding xi on the object latent model for each constant. So we have a third set of parameters that is the set of parameters for all the predicates of the symbolic model. And so we see we have three sets of parameters, theta, tau, and eta. And if we take this definition, then a property latent model can be simply implemented by a Bayesian classifier. And here I have a representation, graphical representation. If probably we would need a convolutional network rather than a fit4, but it doesn't matter. It's just an example. So given a sample in the latent space, then this classifier can be trained to understand whether this is a book or not. Now, before getting to a very, very simple example, where I hope I'll convince you that this is really a challenge, let me state let me enlighten an important point. So, of course, we know very well, there are very well-known methods to train a classifier. There are very good, well-known methods to train a variational encoders. There are very good and well-known methods to understand, to learn the probability distribution of an action by acting in the environment. But here the challenge is that we cannot do this separately. So we cannot trust one, as I mentioned before, and learn the other ones. Really, the learning process of one should be influenced by the learning process of the other. And let me try to explain this through this very, very simple example. And this actually is really a toy example, because the environment I'm going to propose you is probably the simplest that I can. So there is just one object in this environment. So I have just one constant C in my symbolic model. And in this environment, I have just three predicates. In this environment, I have only books and boxes, and they can be just in two states, open or closed. So this gives rise to a very limited, small number of possible states, 8 possible states. But let's suppose that now, while our agent really lives and explores the environment, its object detector gets this kind of image. You know, this is a bit of a strange image because it has the shape of a book, but actually we can understand it is a book. That is also written, Rebecca's memory box. But you know, when it's closed, it really looks a bit like a book. So let's suppose that the object represented symbolically by the constant C, that is actually a box, when it's closed, really looks like a book. So our very good pre-trained classifier would say, yeah, I'm almost sure that this is a book. Then the classifier about the box has some doubts because it's a bit strange, but it's still a low probability. And then the agent is sure that this object is closed. Now, if we want to understand in which state we are, we simply can compute what we in planning call the belief states. So we can compute the probabilities of all these atoms, and we get something like this. So since the agent is sure that is open is false, we get 0 here. And then if we multiply the probability, we get the highest probability in the fact that we have a book, is not a box, and is closed. But now let's go back to this picture. So let's suppose that our little agent that has no manipulation capabilities asks the little girl, please, could you open the book? And so let's suppose that the girl really or someone opens the book, actually opens something that the agent believes it's a book, but is actually a box. And what we get something like this. And now it's clear this is a box, and our good pre-trained classifier should recognize this. So the books, actually the box gets open, we have a new observation. If we have a very good encoder, this will return a probability distribution that is very different from the original one, with the mean and the covariance on C. And so we suppose we could update this normal distribution with the new observation. Of course, here there is a big problem of probably of continuous learning, catastrophic forgetting, but let's suppose that our agent can do this. Then our very good pre-trained classifier, now that I have a very different probability distribution, normal distribution, should really understand that this is a box. Indeed, the result should be this. I'm sure that this is not a book. I'm rather confident that this is a box, and I'm sure that it is closed. All what I said until now is already a challenge by itself, but you know, the big challenge is still to come, because what about the symbolic model, which is the normal, the usual, reasonable background knowledge that I could have about the symbolic model for opening an object? Perceiving a box by opening a book? No. If I open an object, the object can change state, but will not become a different object. So there is a reasonable contrast with the symbolic model. Indeed, the normal background knowledge that we could give to the symbolic model of the agent would be something like this. Maybe that opening will fail or will succeed, but in any case will stay a book, will not become a box. So nothing like this. But our perception model tells us that this is actually became a box. So there is a real problem here. There is a real contradiction between the symbolic and the perception model. So a challenge is how can the agent deal with the contrast, with this contradiction between the symbolic and the latent model. But the challenge is even more challenging because I gave from granted, I have done an assumption that is really far from obvious. So how can the agent understand that this is the same object? Why the agent shouldn't think that, believe that the first is a different object from the second, the first is a book and is closed, and the second is a box and is open. This would be even more in agreement with, or less in contradiction, let's say, with the symbolic model. And think about opening and closing 10 times this object. I could have really 10,000 times. I could have really a huge number of constant and possibly different objects. But let me make the problem even a bit more, it can be amusing, but also a bit more difficult. Let's suppose that when I open the box, I found a ball inside. So I have 3 objects, 2 objects, 1 object, 3,000 objects. If I open 10,000 times this thing. So I would like to have something that is able to tell me, no, I can cluster all the possible constants in just one constant that represent this object when it's closed and when it's open, and I'd like to cluster it in a different constant that represent the ball. So I hope I convinced you that it is a kind of global learning challenge. And this is because I have different steps that should be really put all together. Each step influences the other one. So let's summarize it. I have to do an encoding that is able to represent the different states or different way in which the agent can perceive the same object. Then I have to have a classifier that does the other work around, really is able to distinguish between the different states. And of course, people in computer vision have, if we take computer vision, then this is just an hypothesis, have worked on this problem that is already by itself a problem. But then we have a third element. The symbolic state transition should be consistent, like in the example that I have just shown, with the states that are observed by the classifier that are encoded by this encoding mechanism. And even more, even the clustering of the observation in a set of constants should be such that all the 4 things are in agreement. So the problem is that, as I mentioned before, I cannot trust one of them and learn the other ones, because there is no really reason to trust one of them. But even worse, there is no sequence preference. One could say, well, first of all, I learn how many objects I have in the environment, then I classify them. But of course, this is wrong, because, knowing that something is a ball allows me also to understand that this shouldn't be the same object as a box. So really, these 3 challenges, these 3 learning process should be done influencing each other. So the real point is that these 4 now, not 3, but 4 different parameters that I should learn influence each other, and I should do the process take into account this influence. So I should really learn them jointly. And this is a summary. So I have 4 parameters that should be considered at the same time. Now, let me show some preliminary idea that we thought how to address this challenge. Let's go back to the picture that I like. So I mentioned eta, tau, theta, and c, 4 parameters. So let's this be the internal state of the agent. Let's leave the agent live in this environment, and let's then allow the agent, by perceiving, acting in the environment, to revise, to change these internal states. Let's go a bit more into detail. The internal state of the agent is given by these 4 parameters. Then I have to generate a plan to learn. This by itself is a challenge. So how can I generate a plan such as these actions that I execute, A1, AK, are actions that allow me to learn something new? For instance, if I want to train a classifier to understand whether an object is open or closed, I should close and open the object. This is an idea, but the general problem is really a challenge by itself. Then I should execute the plan, collect a set of observation, and revise the internal states depending on the plan, on the action that I have executed, and the observation. So if you want one formula synthesizing the challenge, believe that the formula could be this: find the loss, find the way in which these 4 parameters are less contradictory as possible, or closest as possible, depending also on pi and O, such that I can define these new internal states. And let me very quickly go a bit more inside all of this. First of all, I have to understand the number of the different constants that I have to have in the symbolic environment. And if I do this with the variational autoencoder, there are techniques that allow us to really have variational clustering. But here, I don't know the number of clusters. So this is already a challenge by itself. Even more, we in planning are used to say, oh, if I have someone that explores the environment, then I find new objects. So the possible constants could increase. But the possible constants could even decrease, because maybe that's something that I thought were 2 books. They become, I realize after that I perceive, I worked in the environment, instead it is just 1 book. So the constant could increase or could decrease. Then we should find a way to minimize the difference between the symbolic transition and the classifier. So if I have a perception of a given state that is obtained by a plan from an initial state, I should do a way in which there is as much less contradiction between these 2 predictions in a way. So minimize the possible differences. 4th point, I should minimize the reconstruction error of the variational encoder and autoencoder. I mentioned before that the reason to have a generative model, there was another reason, not only for interacting with the environment. But, let's suppose that the first task in the clustering of constants tells me that I have 1 object that is a ball, a chair, a box, a book. If I try to generate an image of this strange kind of stuff, the error will be very large. So if I minimize the error, I could help the task of getting the right number of objects. And you see how one of these influence the other. And then a big challenge, planning and acting to learn. So generating informative traces, a trace with states where I get into situation where I can really improve my understanding of the world, my perception mechanism, and my symbolic model of the action. And this general challenge has behind at the base a lot of different challenges that different researchers are trying to address. And for instance, distinguish different objects and object counting in some environment is far from obvious. Online continuous learning, we know very well about the problem of catastrophic forgetting. Planning with an unbounded number of objects is not what we usually do in planning. Usually in planning, we say, okay, the number of objects is fixed, and we have very good techniques for planning with that. Maybe generalized planning could help, but it's far from obvious. I already mentioned the online plan generation of informative trace in the sense that is really an open challenge. Something that I didn't mention in this talk are the last 2 items in this slide. So you remember I said, so let the agent ask to the little girl to open the box that the agent believes is a book. And I said, because the agent has no manipulation capabilities. But you know that opening a book and opening a box is very different. We cannot describe action only at the abstract level of this descriptive level where we say, if I open a box, I open a book, I open a door, then I get into states where the object is opened. Really, to open a door, I need to go close to the door, I need to detect the handle, I have to grasp the handle. So really, there are really continuous actions even with control structure. So I need even a not only a descriptive model, but also something that is a kind of operational model that describe how action is done. And I didn't mention this other problem. So in this very last few minutes, I'd like to tell you about some previous work that I've done with very good friends and colleagues. and that we have even published, because actually what we have done here, we have we have really taken some assumptions. So for instance, let's suppose the symbolic model is correct, let's trust it. Or we don't have perception, we are just at the symbolic level. This kind of assumption to address partially this challenge. But I believe this was the right approach, not only for publishing, but also because step by step to address this challenge. I have no time to go through all this work because, of course, but let me just to say, for some of this works in which way they have some assumption and address partially this challenge that I have described today. And I'd like to start from the seminal paper that Luciano and I published actually at the International Conference of the Italian Association for Artificial Intelligence. So I'm very happy to be here to give this seminar because this was a simple paper because it really worked with very simple perception. The perception were very naive, were just the position of the agent in a given environment, but started to address the kind of problem of learning new states and learning a very perception model. So it was a seminal work, I would say, that started then future research. And with good friends, we have done the work on let's say the problem is too difficult. So let's just consider, let's say, the purely symbolic model and with also deterministic transition that we don't know. And let's do online planning to learn how to generate informative traces. So to generate in the symbolic model a plan that let the agent to reach a state where if I execute an action, I know whether a potential precondition is actually precondition and similar way for the effect. Of course, since the model is not perfect, this plan could be wrong and the actions could fail, but we found a way also to learn from failure, because if I apply an action that is not applicable, I know that in my state, I don't have all the right preconditions. Then I believe that this work was the work that was closest to the challenge I described today, even if I had a very strong assumption. So let's trust a deterministic symbolic model and generate a way to collect autonomously data to train a classifier by planning and acting in the symbolic model. And then we have extended this to automatically evaluate how the model is good. And let me give a simple example. If I have to train a classifier that has to really understand whether a cup of coffee is empty or is filled with coffee, or whether a fridge is full of food or is empty, I have to train the classifier with the images that look at the cup from the top, because if I look at the side, I get random information. And the same, I have to train the classifier after that I have opened the door of a fridge. And I like also to mention this contribution with my two co-authors of the book for operational models of action that I mentioned before. So I have many people to thank, all the people in the previous publication, but especially, I already mentioned Luciano. I'd like especially to thank Leonardo, that now is a postdoc here, and in the group of Luciano, and he actually won the prize for the best PhD thesis of the Italian Association of Artificial Intelligence, exactly working on this topic. Then very good friends at the University of Brescia, Alfonso and Alessandro, very good friends at Örebro University, another Alessandro Safiotti this time, and his PhD student Farid, and my two co-authors of the book about this work on the last problem that I mentioned. So Malik and Dena's PhD student Sunandita. Of course, we are not the only one to work on this topic. There is a huge amount of work. This has good initial steps, a kind of stepping stones that partially address the problem, but I believe that the key challenge is still there, and we should work to address this challenge. And let me just finish 30 seconds on what I believe on a claim. I believe that this problem is much larger, is much a more general problem than the simple kind of toy example that I've shown today. think about healthcare, think about industry. And of course, nowadays, let's take the example of healthcare, but similar can be done for industry. We have wonderful techniques to understand to pre-train very good AI system that can understand whether someone has a disease, that predict even long term the possibility that someone gets a disease. Very useful, incredible stuff. But if you want to put this in the real life, in the clinical practice, for instance, we have continuous data that arrives, and some data is very useful, some data is not useful. Some data should be really taken, other not, in an autonomous way. And a good doctor can tell me, okay, so let's look at the data, but the data doesn't tell me much more. So I still trust in my therapy that is represented in some way, or I should change the therapy, or maybe I should do something different, a different exam to understand whether I should change the therapy. This is a claim, but it's something that we are really experiencing in a set of this kind of industrial or public health applications. So I think the time has gone, and I'd like to finish it. And thank you for giving me this opportunity to present this challenge. Thank you.
So thank you, Paolo. Thank you very much. I think it's now, I can hear some echo, but it's now time for questions. So for the ones of you, the many of you who have attended the seminar on YouTube, I remind you that the chat will be used for questions. So if you have questions, please type them in the chat and I will repeat them to Paolo. And perhaps to start, let's say, breaking the ice, I'm also asking the people here on stage whether they have questions for Paolo.
I have one.
Hi, Giuseppe.
Hi, Paolo. Very interesting talk. Very, very nice work. So my question is the following. You have a lot of uncertainty coming from everywhere. However, you still have a single dynamic model. Maybe you want to have more than one. So one that is somehow the nominal, what you expect the model should be, and then others that are a little bit more conservative, in which you can essentially, maybe you cannot plan, but at least you can guarantee some safety because of these models.
Oh, yes, this is a very good point. Actually, I believe that we could find a general way to find that loss, to define and find that loss. But then what you say probably is something that should be taken into account to give in some way a way to have something that is more important, safety constraint, for instance, and something that will not allow you to find the optimal for that loss, but maybe the safer way. So this is something that should be really understood. That is different from the hypothesis saying I trust the symbolic model. That is usually what we like to do in works on neurosymbolic. I trust the symbolic, I use this. So there is something that I want really not to lose. And this should be taken into account in this way of defining this loss. One interesting point is that if we do this in general to have a much more closer learning between the different aspects, whether this in some way, if I give some background knowledge, this could come for free. But this is really, I'm not sure about this. Maybe there could be different ways. This is a very interesting point because actually not all the background knowledge that I put there, of course I need to challenge it, I need to change, but not all has the same possible weight. So this is a good point to take into account, a challenge in the challenge, I believe.
Any other questions here? But I have a question, for politeness, well, I can go on. So I mean, your question about the ball in the box, made me think it's a bit related with Giuseppe's question. Of the fact that, can you hear me?
No, it's a bit related to, I couldn't hear. No, I can hear you, but I couldn't hear the word.
Yeah, to Giuseppe's question, I think. But in a way, I could immediately see that is a ball and it's a different object, right? But if I were a child, I would need to manipulate it to understand that, I don't know, it's not a bump in the box and I need to touch it, possibly to try to take it out, because if it is really a ball in the box, I can take it out. So even the plan, I mean, the actions to, I don't know, verify or to understand the word are different depending on what is, let's say, your state, and in a way, what is your background knowledge. So do you really believe that the plans that you need to do, or the actions that you need to do, depend on the refinement of your, I don't know, neural net, or the sub-symbolic model that you have learned, depend on the amount of background knowledge that you have distilled? Because somehow I could also say that I understand that is a box because I've learned things that then became my background knowledge, and then I'm applying it to perceive this box. So how can I really, let's say, do this process of learning and adapting the way I also learn new things?
Yeah, so actually your question has many different facets. So one point is about manipulation. So indeed, what the work in interactive perception says is that you really should, exactly as you said, take the ball, move it in order, and also acting and perception is really very connected. And really, to get to that point, I believe that you need to go to the level of an operational model of actions, because the way that we do in planning, as I mentioned before, I open the door and the door is open, is too high level. So I need really to go to that level. So they really are really highly interconnected. And yes, even from your question, the point of planning to learn is depending on also which kind of actions that you can perform is really the big issue. Is really the big issue. We have done this work in a purely symbolic way, making the assumption that we usually do in planning, that we have perception that get translated to the same representation that we used for planning. This is something this is a strong assumption. So yes, the point of having this background knowledge and mixing this kind of thing, I believe, is really a challenge, and should be really manipulation, like other kinds of things that you could do by planning, is really have very, very different dimensions. So I believe that this point is true, and we should address this point. If I understood correctly your question, Chiara.
Yeah. There is a question from the audience. So from Pradik Pramanik, and he says, "Thanks, Paolo, for the great talk. Do you foresee any specific challenges in the context of explaining the robot's behavior with the latent models you have suggested?"
Okay, yes, I could say yes, even if it's, of course, an open challenge itself, even if, of course, explainability usually is not very well formally defined. But for instance, the fact that I have a way to generate the generative model could help, because I generate my interaction in the same language of the environment. I made the example with voice, if I have a question. And then, another point, we have the symbolic model. So if at the end disagree, the symbolic model is a model that has causality. So if I do this, then I know why this happened, because I've done that. And I believe this causality could really add to the typically very good machine learning, deep learning techniques where causality is something that is much more difficult to catch. So yes, I believe it's again that you mentioned an open problem, but that is another open problem that I could list in my slide. But I said there are a lot of specific open problems, and I will do this. But I believe that in some way here, with this approach that is a kind of neurosymbolic, novel approach, we have some help on the direction that you are mentioning.
So, okay. Any other questions from the audience here or from the people in YouTube? If there are no further questions, I would really like to thank you, Paolo. Thank you, all of you, the many of you, for having attended the seminars, all the ones that we watched this seminar offline registered, and for all the students who need a certificate of attendance, please look at the chat, because there is an address for the Google form you have to fill, and you will receive the certificate. We'll have another appointment in a month's time, still for the Spotlight seminars. So stay in tune and you will receive all the notifications for the next one. Thank you.